Hello everyone and welcome back. So this time we're talking about conservative forces, potential energy, and conservation of energy. We talked about power and efficiency last time. Now we're talking about energy this time. Now we're going to be able to use the concept of conservative forces to determine the potential energy of those forces and also be able to apply the principle of conservation energy to solve problems after this class. So actually I want to back up for a second. I want to talk about this picture right here because this is hilarious. This is real. You don't realize this is actually a giant, more or less like crane that's sole purpose was to pick up planes and then have them drop straight face first into the ground. This, or at least one like it, is at NASA Langley. I have seen it, and all they do is they were just trying to study how planes crashed, and so they just lifted them up and dropped them straight face first in the ground. And I'll tell you this, that is honestly a dream job of mine now. So I'm hoping that I get to have that dream job one day. Who knows? Maybe. Okay, but back to it. So why do we care about this stuff? Well, if you look at this right here, we have a bunch of sacks that are going to be depressing those springs. And as we put them on there, they're going to store potential energy in those springs. Now, as the sacks are removed, the platform is going to rise, since some of that potential energy within springs is going to be transformed into a increase in gravitational potential energy of those remaining sacks. Now, if you know the sacks weigh 100 pounds and the equivalent spring constant is 500 pounds per foot, could you figure out how much energy is stored in those springs? Or how about this girl right there? Have you ever seen one of these? I love them. She has a water balloon launcher at the park, and it's pulling back on 4 stretchy cords. Now, if we know the unstretched length of those cords, and we know the stiffness, could we figure out the maximum height and range of the water balloon when it's released from a particular position? Would there be any other information we might need to know? Well, for one, the weight of the water balloon. But anything else? Well, we're going to find out about all of that today, because it is an amazingly helpful tool. Like another application could be roller coasters. If we release this roller coaster, we want to make it sure it can go all the way to the end. It's going to have to go through 2 loops. And when it does that, some of the kinetic energy is going to be transformed into potential energy. And we need to make sure that all of that energy, at least as much as it can be, will make it through. So we might be asking yourselves, well, what is the velocity at point B and C to make this work? And second question is, why is B and C lower than point A? Like, if this was perfectly efficient, could I have them all be the same height? Well, we'll find out. Now, before we can do any of that, we have to talk about conservative force. So a force F is said to be conservative if the work done is independent of the path followed by the force acting on a particle as it moves from A to B. Another way we can think about this is that the work done by the force A is in a closed path. So from A to B and then back to A. Thus we say the work is conserved. Like with that spring, we apply a force and it either stretches and then we let go of the force and it goes back down. Now, the great thing about a conservative force is that the work done only depends on the positions of the particle, and it's independent of its velocity or acceleration. Okay, we only care about the position of the particle. My thing about this is like weight. My guy's going through a roller coaster. Woo! I don't care about the velocity of that guy or the acceleration. All I care about is where am I? That is going to determine how much work has been done by my force, which is gravity. Now, a more rigorous definition brings in potential function V, and some partial differential calculus. And you can check that out in the text. I'm not going to go into a bunch of detail about here. However, even without really understanding those or digging too deep into them, you can understand quite a bit. Because the conservative potential energy of a system is typically written as a potential function V. And there are usually 2 major components that are going to be encountered in our problems: the gravity and energy from springs. So both of these added together is going to be your total potential energy for a system. Now, don't forget that, because we've also learned about kinetic energy earlier. Now we're bringing in potential energy, and surprise, surprise, they're probably going to get combined. So that's it for this time. Thank you for listening, and I'll see you all later. Have an absolutely wonderful day. Bye-bye.